Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to learn how to test hypotheses about the difference in means of two independent populations using a T-statistic. In real life, most of the time, we don't know the population variances when we're conducting a study. And because we don't, we're forced to use the sample variances. If we don't know the population variances, then we can't use a z-test. Fortunately, if the two populations that we're studying are normally distributed or approximately normally distributed, there's a t-statistic or a t-test that will fit this hypothesis test. In testing the differences in two population means, we usually use hypotheses that go like this. The null hypothesis is that the difference in population mean 1 and the difference in population mean 2 is 0. The alternate hypothesis is that the difference in the two population means is not 0, and that's if we use a two-tailed test. Now, these hypotheses are set up to test the zero difference. However, it is possible, and we should make note, that someone might want to, for example, test the difference of say a 5-point difference between mean 1 and mean 2, in which case this would be 5, or you could do 100 or 1,000 or something like that. Most of us are going to use 0, and so today we're going to assume that we're talking about a 0 difference in the population means. If you're doing a one-tailed test, while we leave the null hypothesis is equal to 0, the alternate hypothesis will be either greater than 0 or less than 0. And this would be the case of the one-tailed test. The T formula for testing the difference in two population means is kind of a big formula. And so we're going to write it now and take a look at it. In the numerator, we have the difference in the two sample means. And we have the difference in the two population means. The denominator is kind of long. First part is you have the sample variance times n1 minus 1, and the sample variance of the second sample times n2 minus 1 over n1 plus n2 minus 2. Now all of that is times another expression, 1 over n1 plus 1 over n2. The degrees of freedom formula is n1 plus n2 minus 2. This particular formula assumes that you have equal population variances between the two populations. That is, if we knew the population variances, that the variance for population number 1 would equal the variance for population number 2. Because of this, we sometimes call this the pooled version of the formula, because what's happening here, if you assume the population variances are equal, then we are able to take this part of the formula and weight each of the sample variances and combine them together or pool them in such a way as to estimate the population variance. If you cannot assume that the population variances are equal, then there's another version of this formula that is actually simpler looking, but the degrees of freedom version or piece of that formula is very complex to solve for, so we're not going to use it here today. As an example, let's consider a furniture manufacturing company. The furniture manufacturing company has two different methods or different ways to assemble a given piece of furniture, and they want to test to determine if there's a significant difference in the mean time that it takes to assemble a product using either method. If they assume that assembly times under each method are normally distributed and that the population variances are approximately equal, we can use our t-test to test this hypothesis. Let's look at our null and our alternate hypothesis. As we showed before, the null hypothesis is that there's no difference in the mean assembly times using either product. And our alternate hypothesis is going to be that the difference in the two populations mean is not 0. That is, we're going to do a two-tailed test. And that's because we don't have any idea which of the two methods may turn out to be longer or shorter, like that. Now we're going to go and we're going to take samples of assembly times under each method or each way to assemble the product. And we're going to assume that workers have approximately equal skill and experience in assembling these products. And so we're going to go out under method number 1, and we're going to sample assembly times from 8 workers. And then under method number 2, we're going to sample assembly times from 9 workers. Let's use an alpha of 0.05 to test this hypothesis. And because we have a two-tailed test, of course, alpha over 2 is 0.025. In this particular t-test, our degrees of freedom are n1 plus n2 minus 2. And since n1 is 8 and n2 is 9, that gives us a degrees of freedom of 15. So in trying to determine the critical t-value, as you may recall, we often subscript our critical value with our necessary information. So we have an 0.25, degrees of freedom of 15. And we look this up in the t-table. We get a critical t-value of 2.131. So if we draw that in a graph, the graph of the t-distribution with the mean t in the middle being 0, our critical values on our two-tailed test are a t of plus 2.131 and a t of minus 2.131. So because we're doing a two-tailed test and we have to consider either end or either tail of the distribution, our critical value is actually plus or minus 2.131. So in order to reject the null hypothesis, that is, determine that there is a difference between the two methods of assembling the product, we have to obtain an observed t-value that's greater than 2.131 in this tail or less than minus 2.131 in this tail. Now that we have our problem all set up, we're going to go out and do our study. And we're going to study 8 assembly times under method 1 and 9 assembly times under method 2. Using different workers. So here's the result of the study. Under method 1, we had the following times: 31 minutes, 32 minutes, 40 minutes, 44 minutes, 42 minutes, and 41 minutes. Under method 2, we have 44 minutes, 31 minutes, 33 minutes, and 37 minutes. Now, as soon as we gather the data, nearly the first thing we need to do is compute the sample means. So the sample mean for method 1, for this sample of 8 observations, is 38.375 minutes. The sample mean assembly time for the second group is only 31.56 minutes. Now, even though we use the sample variance in the formula, it's fairly common to write the sample standard deviation first because we're going to square it in the formula. Or you can use the sample variance here. The problem is you've got to be very careful not to square the sample variance again when you put it in the formula. So I like to use the sample standard deviation here, which is 5.78 minutes. The sample standard deviation for method 2 is 5.81 minutes. Now we're going to use this information to solve for our observed t-value and put it all in the formula. Now let's put our sample data in our t-formula and see what our observed t-value turns out to be. Putting our sample means in here, we have 38.375 minus 31.56. Now, We don't know what the difference is in the population means, because if we knew that, we wouldn't be doing this exercise. But we always begin our hypothesis testing problems by assuming that the null is true. So we assume that there's a zero difference, and so that's going to go there. Down here, we're going to have our first sample standard deviation squared times n minus 1, plus our second standard deviation squared, which of course makes the sample variance, times n minus 1 over n1 plus n2 minus 2. And then down here, don't forget this part, we have 1 over n1 plus 1 over n2. When we solve this equation, we come out with an observed t-value of 2.42. Observed t-value. Now let's compare our observed t-value to our critical table t-value. And if you will recall, our critical value was actually plus or minus 2.131. In this particular case, our observed value is positive, so we're going to compare it to the positive critical value of 2.131. Because our observed value in the positive direction is greater than the critical value in the positive direction, then our decision is to reject the null hypothesis. Now let's look on our graph and see where our observed value falls in comparison to our critical value. The graph that we drew before, where we have a mean t of 0 in the middle. We have a two-tail test, so we have rejection regions in each tail with a 0.025 alpha over 2. And our critical values that we looked up in the table were 2.131 and minus 2.131. Now our observed value was 2.42 in the positive direction, so it actually fell out here someplace. We can draw this in. We can come down here, and we can say observed t is 2.42. So, as a rule, if you're in the positive end of the graph, if your observed value is larger than the table value, our decision is reject the null hypothesis. I prefer to look on the graph and visually see where it falls, because the shaded area out here is called the rejection region, and you can see that our observed value falls in the rejection region, and that's how we make that decision. Now, if we have a computer available, we can actually determine the p-value associated with our observed t of 2.42. The tables that we have for t in our text are not complete enough to allow us to do this, but the computer can do it for us. Computer is showing a p-value of 0.0143. Now, the p-value in this particular case is compared to one tail of the two-tail test, because the probability that you have a t randomly generated from this distribution of greater than 2.42 is only 0.0143 probability. So we basically only 1.43% of all t's would fall out here if there was no difference. We set up our alpha to be 0.5, but we split it because we were doing a two-tail test. So we're comparing this 0.0143 to an alpha over 2 of 0.025. If the p-value is smaller than alpha over 2 in a two-tail test, then we have quite rare t. So we either got a very rare t that we got lucky with that occurred with a zero difference, or we conclude that there actually is a difference in the two methods, and that's what we decide here. So our decision is that there is a significant difference in the mean assembly times between method 1 and method 2. Now, if we go back and examine the means from these two methods, you may recall that the mean for method 1, our sample mean, was 38.375 minutes. Our sample mean for method 2 was only 31 minutes, 31.56 minutes. So we can see by going back and observing our sample means that method 1 took longer to assemble on average than method 2, and we've demonstrated through statistics and through our methodology of hypothesis testing that there is a significant difference in the population means were we to have all the values.